Okay, so let's begin with the session. Janani will be joining in 15 minutes, she said, so, because of some issues. Okay, so hey everyone, I am Kirthika Srinivasan from ECE batch of 2022 in the 90TG, and I will be the host for today's huddle on VLSI, analog IC, and computer architecture. So I hope that we all have a very informative discussion about VLSI and whatever and what are the upcoming fields within this topic. So next slide. Hello. Yeah. So I would like to introduce today's panel speakers. So firstly, we have Himanshi Gupta from ECE batch of 2021. She's currently working in Micron. And next we have Shreya Dasgupta from EEE batch of 2002, and she's currently working in analog devices. And then we have Harini Muthukrishnan from EEE batch of 2013, and she's currently working in NVIDIA. And then we have Janani Ramjee from EEE batch of 2020, and she's currently working in Cadence design systems. And then we have Navya Vijayan from EEE batch of 2020, and she's currently working in Bajaj Auto Limited. And then we have Nandita Sreekumar from EEE batch of 2020, who's currently working in NVIDIA. So now, just to break the ice and get things started with, next slide. Yeah. So today's session we have a deep dive into tech, where each of our speakers will be talking about different topics, that is digital design, analog design, and front-end design, verification, back-end design, and computer architecture. And in between these talks, we also have some icebreaker activities planned, so that we can get to know each other and basically understand the different topics within this, and also to just improve your understanding of these fields. So let's get started. And so first up, we have a word cloud, for which I would like to request all the mentees and attendees to go to menti.com and use the code that is displayed on the screen, so that you can enter this word cloud, or we'll be putting the link in the chat box, so you can also access the word cloud using that link. I'll post it now. So basically, in this word cloud, you have to think about, when you think about the word VLSI, what are the topics that come to your mind? I will put the link now.
I was part of that, and a couple of them are really part of that. And then we took some break, and then I started reviewing that, and then some of them took the break. So it's all the hard work that we are doing, which also includes all the interns which is part of this call. It's about the lessons learned, the what's an experience and stuff like that. Let me start here. If you have any questions for the presentation and tech, please let me know, or else we can move ahead with the next topic. Yes, so now this is 29th July, right? So 29th July, right? 29th July. So we would like to VTCT tech leads is something around 26 and 27, and probably within 26 to 28 we try our level best to travel see how it goes.
I'm really sorry about that technical glitch with Mentimeter. I will share my screen now. Is my screen visible?
Yes, it is.
Yeah. Okay, nice. So, large scale fabrication, very large scale FPGA, electronics, logic gates, MOS transistors, very large design flow. Good response, guys. If you can think of any more words, also please keep filling in. Okay, yeah, I can see it's getting updated. That's nice. CMOS, electronics, transistors, ICs. Okay, so what is the new word? Okay, transistors. Okay, nice. So I can see that many of you already have some some basic understanding about what VLSI is. So now we will be having a lot of talk sessions on each of these individual topics like understanding further about VLSI and the different fields that you can work on as either in a company or to pursue research or hires. So stay tuned and let's look. And I really look forward to an informative session today. So let's begin with the talk. So firstly, we have. Okay, I'll stop sharing my screen now. Sandhya will continue sharing. Sandhya, can you share your screen from the next slide? Next slide. Yeah. So now Himanshi will be talking about memory VLSI and over to him.
Thanks, Kirthika. Hello, everyone. My name is Himanshi Gupta, and I'm a EC 2021 pass out, and I currently work as a DRAM design engineer at Micron. I'm choosing to specifically talk about memory VLSI because memory VLSI, the normal flows that you see in the industry are kind of different from what you have in memory. And in my 1 year of experience, I just want to share what I've explored till now. So, can you move to the next slide, please? So, when you think about the semiconductor industry, I think some of the things that first come to your mind might be, processors, microcontrollers, and obviously there's definitely memory. And among memory and storage, in the last few years, because of AI and demand of high computation, the memory industry is something that is on a boom, I would say. And so, in this, I have just tried to give you a perspective of what the current memory industry looks like. And if you see the graph in terms of revenue wise, DRAM, that's the memory, the 128 a GB RAM that you talk about in your um, different scenes, and then there's NAND. NAND is actually the storage that you have in your system. The SSDs and different part of it. So if you see, these two are the major memories that kind of dominate the memory VLSI industries. And apart from that, there are like several emerging memories used for um, many applications. But for the scope of this session, I would dive deeper into DRAM because that's something that I work with currently, to give you an overview of the applications of DRAM and where you can actually employ your skills that you learn as an undergrad to become a DRAM design engineer. Next slide, please. So if you see here, this is here I've just shown the different applications of DRAM, but memory as a whole has a versatile range of applications. In any electronic system, right now, memory is a huge requirement. The demand for high bandwidth, the demand for low power memory, and the basics of VLSI. And if some of you would know that memory kind of becomes the bottleneck when it comes to system wise performance, and that's why it's extremely crucial that the development in memory takes place. And so if you see here, the DRAM based like, let's not go into too much technical terms, but just to give you a sense where DRAM is employed, from your mobiles to your PCs to your servers, and even with the advent of self-driving cars, and a lot of automotive industry is using memory on a very wide scale. And obviously there's your data intensive systems like your graphic cards, AI. So essentially my the crux is that memory is used literally everywhere. So yeah, can you move to the next slide, please? So when you say a DRAM design engineer, so what do you do? So technically, so obviously the speakers coming forward would speak about analog design, digital design, but memory is, especially DRAM memory, is a space which is a very good opportunity for mixed signal design, because memory does not have any logic. Memory is mostly consists of asynchronous blocks, each part performing different functions. So a DRAM die has plenty of analog and digital circuits. And what becomes very crucial in memory is um, you have to really model, like I said, because things are of asynchronous nature. Therefore, to when you talk about speed and bandwidth, it's very important that you know how to model all the parasitics that are coming into the circuit. By parasitics I mean, so you would know about long metal routes, right? Whenever you're forming a chip, you have long metal routes, because of which there can be some parasitics, that is the RNC component coming in. So essentially parasitic modeling and design validation is necessary. And also, interestingly, as a design engineer, you also do the first level of verification. So you also like play along with modeling the different circuits, and then doing a whole lot of simulations, be it like analog simulations, verilog simulations. So you basically get an overview of everything. And so this is specifically about memory circuit design. But in the memory VLSI industry, apart from circuit design, you have plenty of other opportunities, such as signal integrity, technology development, which basically talks about each layer of how the memory is built, and then common things like layout, verification, packaging. This is present in all, like both logic as well as memory industry. But then there are various aspects to it, is what I wanted to mention. And here I've listed out some major DRAM manufacturing companies. Because you can literally count them on your fingertips. So Micron, SK Hynix, and Samsung are some of the pioneers in the DRAM manufacturing industry, and that's something you can look forward to in case you're interested in making a career in memory design. Next slide, please. So as a fresher, honestly, being getting into a memory design engineer would not require a lot. It's always about the basics. So if you want to become a memory design engineer, essential knowledge of CMOS circuit design, something that you would already studied in class, basics of amplifiers, sequential circuits, and also a good knowledge of the device physics of MOS, how a MOS works, or the basic structure, and how the channel is formed, things like that. If you're clear about that, that can be a very good place to start with. And having prior knowledge of HSPI simulation is the bonus. I mentioned that because, like I stated in the earlier slides, modeling is something that is very crucial when it comes to a DRAM circuit design engineer. And apart from that, basics of Verilog is important when you're doing the first level of verification. And the last two things that I mentioned, I think anyone in the industry would agree with it. A basic acquaintance with Linux. You don't have to be the master, but then simple file handling commands, as well as any shell scripting language of your choice, be it Python, Bash, or Perl. The basics of it, if you know in college, would really give you a head start in industry, because that's something that's very extensively used. And I've just quoted a couple of books regarding memory in case you're interested. So yeah, you can read more about it and see if it interests you. And that's it from my end. And I'll be happy to take any questions in the end. Thank you.
Thank you, Himanshi, for that very insightful talk uh, about memory design. So, guys, if you have any questions in mind, you can put it in the chat box now. If you have any questions for Himanshi. Feel free to ask questions, because that is how we can really improve our understanding and gain a lot of knowledge. So, guys, any questions?
Okay. I see upcoming new technologies in memory design. Um, well, there's a lot that keeps going on in background, but something that the industry is looking forward to is CXL-based memories. So there's been a recent development in the bus architectures in computer systems that have been used. So based on that, it's like a high bandwidth memory to kind of cater to the needs of accelerator based systems. So that is something that's coming out. Samsung has already released one of it. And apart from that, the DDR continues to evolve. As you might be aware, there are DDR1, 2, 3, 4, 5 memories. So DDR5 and DDR6 is something that the industry is looking forward to. Can you give a brief idea about Verilog? So, I mean, Verilog is basically a language which is kind of used to model your, what do I say, combinational and sequential logics. I think in the upcoming slides, you'll be talking more about Verilog. So I'll just leave it to the speakers then. How do we start learning Verilog from scratch? Again, I think it's covered in the upcoming slides, but then there are plenty of resources, and something that I followed was a book by Samir Parnitkar. It has some very good basics to start Verilog. And what are your thoughts on processing and memory solutions? Are they being widely explored in the memory industry? Um, Processing and memory solutions, yes, they're a very interesting field, and something that has, I mean, they are being looked upon, but they're not really in this stage where it's more viable to be launched as a product, because neuromorphic computing and having memory near the processing power is something that I personally have not seen being actively researched upon, but I do feel there is quite a scope of doing that, be it in terms of close-knit packaging or enhanced performance. Um, I think that's about it. Thanks for the questions.
Okay, there's another question, Himanshi.
Resources for Perl. I currently do not recollect, but then if you search on the internet, I'm sure there'll be pretty much a lot of courses on Coursera or even YouTube for that matter. I'm sorry, I do not have a specific reference in mind.
Okay, I think that is. I think we have covered all the questions. So, thank you so much, Himanshi, for that very wonderful talk. Now, moving on, next up we have Navya, who will be talking about analog design and her experiences in working as as an assistance manager in Bajaj Auto. So over to you, Navya.
Hey everyone, very glad to be here. And Himanshi, that was very insightful. So, so I'm Navya Vijayan. I work as an assistant manager at Bajaj Auto Limited. So, Bajaj is an original equipment manufacturer, and recently we have gotten into the space of EVs. So, I'll be covering a lot of EVs in the upcoming slides. So, moving on to the next slide. Yep. Okay, yeah. So analog hardware design is basically the design of control and power circuits for a wide variety of applications in spanning industries like the EV industry, automotive, telecom, aerospace, and so on and so forth. So specifically, since I work in the EV industry, I've mentioned a few control units that go into the. Could you go back? Yeah, this slide. I've mentioned a few, control units that go into the electric vehicles. I've just put on Chetak's picture here, our recent two-wheeler, but then this is basically common for any EV that you see. So there's the vehicle control unit, different control units like the vehicle control unit, which is basically the, you could call the central, system for the entire vehicle. It acts as a bridge between the various control units that I've mentioned here. Then we have the motor control unit, which actually controls the motor that drives your wheels. We have the charger and the residual current device. These two go into the AC charging system of the vehicle, which basically fuels your vehicle to go forward. Then we have the battery management system, which ensures that your batteries are working at the correct potential levels, cell balancing is done properly, and so on and so forth. So analog design in each of these control units basically means that you get your product is a PCB. So unlike all of these speakers who are here, the product that I design is not an IC, but it is a PCB. So moving on. Yes. So I would like to touch upon a few basic of a basic flow chart that we follow for our designs. So the first thing for any designer would be to drill down to the hardware specifications from the system requirements. So you have something called as a system requirements, which comes from the systems teams, or you yourself make it if you're initiating the project. Then you go on to making a block diagram of your control unit, incorporating the various functionalities that the control unit should be doing. Thirdly, you have the design calculations and simulations. This is where you delve deep into the design itself. You have your various blocks that you have already done, gotten from the block diagram. You delve into each block. You go into the design specifications, design calculations, and simulations for each block. And then the next step would be, once your simulations are ready, once you know that at the simulation level, at least your control unit is working, you go into the schematic makeup. Schematic is basically a drawing that your PCB engineer needs to make the PCB, PCB layout, and then further on to make the PCB itself. The fourth step is PCB designing. Now, this is something that the industry has a separate, workforce for. As an analog design engineer, you won't be really doing the PCB designing, but your work probably before PCB designing, like it ends here. You make the schematic and pass it on to the PCB team. The team decides the routing, the layout, and all of that. But of course, you'll be very much a part of the PCB designing and PCB design analysis as to if your routing is correct, if your the track width and all of that is being maintained properly. So you'll very much be a part of the analysis procedure, but not exactly the design itself. Then once the PCB your PCB design is done, your Gerber is released, and you get the board with you. You do get on to testing. You make the test plans, functional testing, failure simulations. Then you have various environmental testings, according to the standards. This is especially true for industries like automotive, aerospace, and all of that, where you follow very strict standards. And you have the EMI EMC, which is also EMI EMC, which is electromagnetic interference and electromagnetic compatibility. These tests that you do. And then finally, once your product passes all of these tests, it goes into the release phase, where you push out the product into the vehicle and which eventually goes into the market. Yeah. The next slide, please. Yes. So, like I mentioned earlier, unlike the work that most of the speakers, all of the speakers that do here, I do not design an IC. What I do is design the PCB. So, for people looking to get into this space, which is core analog design, you have to understand that your product is a PCB and not an IC. So the skill set that is needed, though the basics remain the same, you would probably not have to, have a very deep understanding of the tools like Verilog or, languages like VHDL. What you would basically need would be a very intuitive as well as an analytical knowledge of circuits and various electronics components like both capacitors, resistances, inductors, which are your passive electronic components, and active components like MOSFETs, BJTs, IGBTs, and all of that. And you should definitely have knowledge about simulation softwares like SPICE, MATLAB, etc. A knowledge of power converters would be, I wouldn't say a bonus, basic, you should really have a grasp of your power converters at the basic level, like, DC-DC converters, AC-DC converters, inverters, rectifiers, and all of that. Yes, moving on. Yeah. Now, this is something that I would like to, I wanted to touch upon. Could you go to, yeah. Yes. So, as in the EV industry especially, and I think this is true for many other industries as well, in the analog design space, we are what people call the original equipment manufacturers, that is the OEMs. So in OEMs, there are basically two kinds of, I would say, job roles that a fresher can look into. The first one would be that of a designer. So when I joined Bajaj, for a large part of my career, which is, I'm just like 1 year, 4 months into the company. So for a large part of this time, I worked as a designer. And in here, what, I was involved in the making of something called as the lighting controller, where basically a PCB that controls the entire functioning of the lighting system in the vehicle. So in that, the responsibilities a designer would have would be to design based on the specifications that are given to you, get it tested, make the PCB made up, and then release the product. You're part of the entire designing process from the scratch. Another role in the OEM industry, which works in technology like EVs, aerospace, and stuff, is what you can call a program manager or a vendor manager. So that person would be responsible for getting the designs done from a vendor. The OEM contacts the vendor. The vendor is the person who, the vendor company, teams in the vendor company are the ones who design the product. So what your work as a vendor manager would be to get the designs done from the vendor, while being a part of the design process, very much being part of the design process. So you analyze the designs that they make, find out debug the issues that they face, suggest your ideas, then make test plans, and also make sure that you get the tests done at your end, make sure that they do the testing as well. So I would call it an end-to-end product development role. So for a huge part of my career here, I was a designer, and then I moved into a vendor manager role where, right now I am having to actually deal with a lot of vendors. Not a lot of vendors, actually a vendor that is responsible for making my product, that is the RCD. I mentioned that in one of the slides before. So I would say the role of a vendor manager, includes a lot of management aspect as well, apart from having a strong know-how of your technical, details that are relevant for your board. So yeah, I think that brings me to the end of my presentation. I'll be very happy to take questions if you all have any.
Thank you, Navya, for that very interesting talk about analog design, especially in the EVs field, and also the different job roles that we have in this industry. So, guys, please feel free to put any questions you have for Navya in the chat box. Okay, so guys, if you like at the moment, if you don't have any questions, also it's fine. At the end, also we have a small Q&A session with everybody where you can put questions that you have in your mind. So let's move on. So next slide, Sandhya. So now we have a small icebreaker activity. So this is basically like a small quiz about, it's like a pop culture quiz on VLSI. Like, what are the popular products and, upcoming developments. So I would request all the attendees and mentees to go to menti.com and enter this code that is displayed on the screen. Or you can also join using the link that I'll be putting in the chat box now. So, yeah, so I've put the link in the chat box now. You guys can join, please. Sandhya, are you sharing your screen? It's not visible right now, actually.
Yeah, one second.
Okay, okay. Press. Refresh the page. I think that's what is creating an issue. Just press enter to go to the next question. Oh, can you sorry for that background noise. Can you move your mouse to the right corner? Maybe there is an arrow. The questions are not appearing actually. Wait, yeah, I think some questions got skipped. Okay, so which was the world's first touchscreen smartphone? So we have three options: iPhone, IBM Simon, or the LG Prada. So you have 7 seconds to answer this, guys. Yeah, so it was IBM Simon. Actually, most of us assumed that iPhone was the first smartphone which came with a touchscreen and all that. But actually, IBM Simon was released almost 10 years before the first iPhone. But the thing was, iPhone had a touchscreen which was more user friendly, and that's why it became such an iconic product. So let's. I'm actually quite surprised that everybody knew the right answer, but it's good.
Me too.
So yeah, next slide.
I didn't know this either. So I was like, oh, okay. Everybody's very aware.
Yeah. Uh, Sandhya, go to the next slide. But I think, okay. Yeah. Oh wait, that question. Okay, I think that was a fourth question, but it came for the third, I guess. Okay. I don't think Amazon was a smartphone though. Yeah, like I meant the touch screen technology. Like smartphone, obviously, yeah, it has so many other features, but I meant in terms of the touch screen, like the transition from the button cell phone to the touch screen. Yeah, I'll check it out as well. Okay, I think there is some technical glitch with Menti.com actually. That's why the slides were not changing the way we wanted it to. So I guess let's just move on. And thank you so much for your participation. Thank you so much everybody for your participation in the quiz, and I hope it was informative and something new. So let's move to the next talk. Next slide, Sandhya. So next up we have Janani, who will be talking about front-end VLSI design. So over to you, Janani.
Am I audible?
Yes, yes, you're audible.
Yeah, thank you. So hi guys, I'm sorry I was a tad bit late in joining the call. It's quite early in the morning here. So, and my name is Janani. I'm currently interning at Cadence Design Systems. I work for the Tensilica line of processors. I'm so uh, when I have to talk about front end VLSI design in general. So the flowchart which I have given you is probably the flowchart which you study in your sixth semester VLSI design if you're in AAA. So this is the flowchart that most of it's a very generic flowchart. You have some details in it, but this is the general flowchart that any semiconductor company in the industry actually follows. So in general, right? I have boxed it in a different way. So you start from specification, you go to high level design, you go to low level design, you go to RTL coding, you go to functional verification. And some companies stop it with functional verification, and the logic synthesis is a kind of a mix between front end and back end VLSI. But again, uh, we also in my present company, we still consider logic synthesis as front end. So the job is on me anyway. So I know added it with a box and a warning saying some companies consider it back end and some companies consider it front end. It's kind of a mix, or and some companies don't classify it at all. It's like it's both of your jobs, both of you do it together. That's how it works. So in in and yeah, so like there is one meme going on now. So like there are these two oldies, saying jaga hai and jaga nahi hai. That's basically like the design engineer is saying, you really have space, and the backend engineer saying, no, you don't have space. And yeah, it's true, it happens. Like when we communicate back to the backend engineer, he'll be like, bro, there's no space here. It's like, we'll be like, no, bro, can you just squeeze it somewhere? Use probably a better technology library. Just squeeze it in there. Like, this is how the conversation goes. So, yeah. So, coming back. So, uh, so for an front-end VLSI designer, you start with the specification. So specification is basically like your team's compact. Your team leader will probably be a expert in computer architecture, and so the specification is made like this, right? So it is a mix of innovation and customer requirement. So. Uh, I work in a IP core supplier, semiconductor IP core supplier. So semiconductor IP core suppliers basically are more of designing based on customer specifications. So and a bit of your own innovation, because you should stand out in the crowd. So so that's basically a place where we've decided, okay, so we are implementing this, and we are like, the customer wants this. So you integrate and sort of make a specification saying, we're finally going to make this block. And then comes the high level design. So what are the sub blocks in the block? So how are we going to split this? So because not it's not a single man's work making any core, or for that matter, it's not a single man's work. You have teams, you have sub teams doing it. So you split the work. And then low level design. So after you have split it into blocks, saying, and now you define the micro architecture of each block. So taking this signal, I'm using this signal as a correcting signal. I'm using a parity signal. I'm kind of pulling it from here and pushing it this side. Like, yeah, I mean, I'm talking in very generic terms, but basically, the low level design is where I tend to see low level design as gate level design. I had this professor who always says, when you start coding, right? You need to draw gates by hand and then do RTL coding. He still says that. He is a professor who is in this industry for more than 40 years, and he has a great name. And he still says, if I ever see you guys doing an RTL coding without drawing it gate level, I'll I'll straight away throw your project to the dustbin. That I'm talking about designing a neural network engine, and he wanted gate level, like he wanted us to draw gates by hand. Yeah, so that's like low level design. You want to use how are you going to design the logic that's of the each of the block. And then you have RTL coding. RTL coding is where your HDLs, hardware description languages, comes into play, like VHDL, Verilog, System Verilog, etc. And uh, so the last two parts are the most important parts of the industry. So you code and you verify. You code and you verify. This is how it goes back and forth for some time. And then that's where technically every company stops its front end process, and synthesis is basically the designer and the physical designer, I mean the back end engineer, trying to so so back end engineers are called physical designers. So we both sit together, and it goes back and forth, saying the same thing. It is kind of the meme situation. Yeah. So that's the flow of we call what we call as the ASIC design flow, and this is what happens in the front end. Can you go to the next slide, please? Thank you. So, types of semiconductor companies that hire in terms of job opportunities, you have the semiconductor IP companies. I work for one, and you have fabless semiconductor companies. So, fabless semiconductor companies, you have like Apple is. I don't know if they have a foundry. So let's go with something like generic. I think. I think Samsung doesn't have a foundry, if I'm right. Yeah. So the companies which manufacture your cell phones, but basically they outsource the actual manufacturing to a foundry and you get the chip back from them. They are like basically a fabless semiconductor companies. You send them the design, they design it for you and send it back. Like they make it into a physical design and they send it back to you. That is your fabless semiconductor companies. Basically, the company does all the designing hard work, and another company does the manufacturing hard work. That's it. And all in all, semiconductor company, the best example is Intel. So Intel is like Intel has like it starts from computer architecture until you know materials engineering they are into also. So yeah, they have a they do everything together. So they have also that's like an all-in-one semiconductor company. They have everything. So what are the skills you are expected to have? So be thorough with digital design and Boolean algebra. I mean, that's like base, man. So uh, even now, right? Like on a day-to-day basis, you will use your AND gate, OR gate, muxes, and flip-flops. So that's like a very basic, thorough knowledge, basic knowledge of combinational and sequential logic circuits is essential and necessary. Be confident with one hardware description language at least, be it VHDL, Verilog, System Verilog. You have newer ones also, Blue Spec System Verilog, Transaction Level Verilog. I mean, they are just evolving, especially TL Verilog. Blue Spec has been in the making since 2006, and Shakti processors that is being developed in IITM, they use Blue Spec. So, but yeah, I mean, in that's still academia, right? You're in the industry, it's still system Verilog and Verilog because it's like it has an IEEE standard. It's being maintained in a very global way, and so yeah, you still have that going on. But yeah, I mean, companies are also trying to, take in Blue Spec. Blue Spec is being marketed a lot, so yeah, you can watch out for that. I mean, learning that is really a good asset because I have seen a few companies bending towards Blue Spec, and yeah, and be good with your basic computer architecture concepts. I mean, see, computer architecture concepts is like you have way too many YouTube videos to help you with that. Even if you browse YouTube, just type computer architecture, you will get some really good videos. Like people out there are doing fantastic jobs, so you can go ahead and do that, and be familiar with design concepts like this is quite a high level. I mean, for generally for bachelors, they don't expect you to know stuff like this. But no, if you're really interested in like a full-fledged career in front-end VLSI design, I mean, there is no limit to learn, right? So you can go with like learn about design concepts like clock gating, how do you do asynchronous data transfer, how is pipeline designs done, and so on and so forth. Yeah. Think next slide, please. Yeah, so I made this slide because what is your motivation to be a front end VLSI designer? So my personal motivation is my brain is in churn daily. Okay, so and my brain still uses what I learned in my third semester of BTech. So every day, so it's like it's fun, right? Like sometimes it gives you like my guilty pleasure is to so just do a mux with logic gates and those kind of stuff. Like I have my super, like one of my supervisors, he just posts design like a circuital question, make this circuit only with NAND gates, only with NOR gates. I'm saying NAND and NOR because they're called universal gates for a reason. So he just puts the questions out. We keep ourselves, our brain churning, right? Why can't we design it like this? Why can't we design it like that? So your brain is daily in a churn. You daily design something, and at the end when you go to sleep at night, you'll be proud of saying, oh, I designed this circuit, I designed this. It might be just be a small counter, but still you'll have the satisfaction of you have done something at night. No, I've designed something. So that's something, that feeling is exhilarating. So that's your basic motivation to be a front end VLSI designer. Next slide, please. Thank you. Yeah. So this These are like a few references which are like Bibles for any front end VLSI. For that matter, if you want to be in the VLSI industry, these five things are, I feel, very important. So there is this YouTube channel where called by it's being handled by a very great professor at ETH Zurich. His name is Professor Onur Mutlu. That man is like a genius and an encyclopedia himself. So he has done extensive research in computer architecture, digital design, memory design, and his and now he is into like he is merging biotech concepts to computers, and he's doing a lot of stuff. So you can just check out his videos. And he records every one of his class and he puts it on YouTube. So basically, it will be like you're studying in UTH Zurich without paying him. So that's nice. And yeah, so the other link which I have put is actually one of my own professors' link, and he was like one of the reasons I wanted to go to NC State. So, like, his name is Dr. Paul Franzen, and if I'm right, this playlist contains your go-to stuff for Verilog, basically, and how in an industry how the Verilog stuff is done. It's quite an advanced course, so you know if you go step by step. You first watch Onur Mutlu's undergraduate digital design course, and then you go for this. And that's like something for you if you want to get into RTL design. Digital design by Morris Manos. I mean, this is your, yeah, again, your basic digital design textbook. That you need to be very thorough with. And then you have this Verilog HDL guide by Samir Palnetkar. Yeah, I think Himanshi mentioned this. So yeah, so this book is like this book goes way back, man. 1990s it goes to, and but it is still being used because this is like one wholesome guide. You have good examples of finite state machines being designed and how they do stuff. There is this one beautiful example of a traffic controller in that. So like that is one extremely wholesome example. If you understand the traffic controller, probably you'll be good to go for a long time. And then you have Computer Organization and Design by David A. Patterson and John L. Hennessy. This is like a great book. Prefer you to read the Risk 5 edition. They have a MIPS edition, but it's good to go for the Risk 5 edition because Risk 5 is like currently the in thing. Everybody is like Risk 5, Risk 5, Risk 5. So, try going towards that. Yeah. I think that's all from my side. Any questions, I'll be happy to take. Thank you. And yeah, sorry, there was this one question in chat about a Perl reference. So yeah, so I use Perl extensively, and the Perl there is something called as the Camel Book by O'Reilly. That book is like a Perl guide or something. So I mean, that's like and that's vetted by Larry Wall. So Larry Wall is the founder of Perl. Perl was basically found by this NASA astronaut because he was tired of scripting in other languages at that point of time. He said he wanted a simpler scripting language and he wrote Perl. Yeah, big innovations come in that way, right? So he wrote Perl, and this book is actually his own personal guide. He actually kind of anybody in the industry who wants to learn Perl, they use this Camel book. If you just type Perl Camel book, you'll get it. Yeah. Thank you.
Thank you, Janani, for that very insightful talk. Yeah, okay, we have questions. So, in your opinion, is it advisable to pursue an MS in VLSI abroad right after your BTech, or it helps to get industry exposure for a few years first? Actually, this is a question even I had in mind. So, uh,
Okay, okay. I'm quite biased here. Okay, I went directly after my BTech because I really did a lot of research work when I was in my bachelor's, right? I did an on semester in at college, on semester project at college that involved uh, see the college people, right? They do really good stuff. So if you get involved in those things and you expose yourself to all the kind of varied facets of VLSI design, and you decide that this is your life, like this is your career path, then might as well just go for a master's and get a master's degree and specialize in that. Who knows? Master's degree might lead to a PhD also. So yeah, so I'm quite biased. But I do know that my friends who have got industry exposure, they find it a bit more easier to smooth sail their master's degree. And yeah, I mean, it's personal preference more than uh, uh, you can say, like uh, an advice. So it's your comfort level. Do you feel that a master's, I can do it, I can, I have learned enough, like I have quite a few confidence enough that I can sail through a master's degree, I know I want to specialize in this area, then go for it, go do your masters and pursue your career in that. You still want to look at whether you want to do a front end VLSA or a back end VLSA, or you want to go into core computer architecture, or you want to go into materials engineering in the semiconductor foundry. You want to explore all your options, you might as well take up a job in the industry, experience it firsthand, and then pursue your specialization. That's my view about it. Yeah. Thank you.
Yes, I really answered some questions. I mean, even I had a similar question. So thank you for that. Any other questions? Please feel free to ask and put it in the chat box. Or you're even welcome to like unmute and ask questions because. I think that is all in terms of questions. So thank you once again, Janani, for this talk about front-end VLSI design. And I hope it was very informative. And next up, we have Shreya Dasgupta from Analog Devices, and she'll be talking about VLSI verification. Over to you, Shreya.
Thanks, Kirthika. I think all the talks so far have been so good that even I'm getting information out of it even now. So verification, it's a very vast subject really to cover, because as everybody was going through their respective sections, Himanshi, Navya and Janani. So when Himanshi was talking about memory design and mixed signal design, I was thinking that, okay, there is a verification arm there which needs where the people would be doing mixed signal verification. Then in case of Navya, when she talked about PCB design, though that itself doesn't need the verification that we talk of within an IC, but a verification engineer in an IC company has to think of all the use cases that the chip could be used in and verify it in that form. And of course, Janani, when she covered digital and core verification, that also needs verification. So verification is really large. So I'm going to try to give a very short this thing related to what my career has been about. So just to start off, there is always this misunderstanding that verification is testing, but and maybe as far as English goes, yes, verification means testing. But the thing is, verification is a completely different skill which has to be developed. And not only is it a single skill, it is a, depending on what you are verifying, you need either digital understanding or analog understanding. And depending on the field you're in, what final end product your chip is going into, you need to understand that also. So very loosely speaking, a verification engineer codes models or rules according to a set of specifications. So when Janani picked up, showed that flow of front-end design, the first thing was specifications. The same thing would come to a verification engineer, where the verification engineer would then code rules and models that satisfy the specification. And when the design is available, he or she would put these two together and see whether the design is compliant with those specifications. And this whole process, the rules and models vary depending on the field. So maybe as I go through the talk, it will be a little more, some aspects of it will be clearer. As I said, it is not testing. And why verification? Of course, it is this diagram on the right, that little triangle. Design complexity is growing at a breakneck speed. I was just looking at, okay, 7nm, what is the size right now? So the 7nm, this thing that I looked on the internet, it says there are 20 billion transistors on a fingernail space, where you can't imagine the amount of logic, the amount of things that have to happen on that. And the tricky thing is the right-hand arm, which is technology cost, that you have to make this happen at the first shot, because for manufacturing at different technology nodes, as the nodes are going lower and lower, the cost is just going through the roof. So 180nm is very old. At 180nm, a mask set used to cost $10,000. Now at 28nm, so 28nm is the last stable technology, there it costs about $1.5 million. So 7nm, I didn't get into how much it costs. It's still in research. But you can imagine that if you design a chip and you're going to press a button to send it out for fabrication, and you're spending $1.5 million on it, it better not come dead. It better work. It better fit all the specs that it is supposed to fit. And some of them are really complex, where there are teams of 50, 100 engineers who are designing that. So verification is like a parallel team of sometimes twice, sometimes 1:1, this thing of people who are verifying that same design using their own languages, methodologies, and tools. So as a verification engineer, that methodology is something that keeps evolving. So we've covered why verification is needed. And now I'll just go into the different skills that I have had to go through in my career path, okay? Because as I've just said, the skills will differ depending on whether you're going into a memory design company or a large digital design company, or in my case, analog devices. We have chips which sit on that edge, which interface with real world and then convert it into digital. So it has analog as well as digital content. And I just wanted to clarify one thing, is that this career path and skill path, sometimes you feel like your career is not moving because you're not moving to the next grade, or you don't know what is happening. But the skill path is something that you definitely, it's slightly more in your control, and it is something that you can always bring up in these conversations that happen either in interviews with a new company or interviews with your boss once you join, where the person asks, where do you see yourself 5 years from now? I've really found that a very odd question, because sometimes you don't even know what is the possibility, right? But I found that addressing it from the skill side of it really helps, because if you started working and you see somebody else working in something else, you can always say, I want to pick up that skill, or I want to change my methodology to something else. I want to do synthesis more, or I want to get into the mixed signal side of things more. So separate out the skill that you want to pick up from your career, and any skill that you pick up will always be useful. So I started off as an applications engineer. I worked for 2 years in application, but that skill that I had in application now give me the understanding of how chip debug interfaces work and things like that, which is something that is important for, IC. A whole set of requirements for an IC comes from how it gets debugged, which doesn't come into the final customer's set of specs that the customer drives. But it's very important, because unless you can debug your application or figure out whether your analog ADC is working on the chip, you cannot basically sell anything. So the applications was the first couple of years. Then 2004 to 2007, I started working in verification, and it was on a methodology or language called SpecMin-E. Now, this is another thing that I have figured, that as a fresher, you need to know one basic language, whether that's C, whether it's Verilog, or C++ in case you're in, that's great. But the methodology and language, especially on the verification side, has been changing constantly. So on the design side, things have been fairly stable. Analog, SPICE, HSPICE, LT-SPICE, it's been almost similar like that for as long as, 20 years, with more and more features maybe. And on the digital side, System Verilog is one thing that has hugely come up. System Verilog is also the skill that we look for in verification engineers now, but as a fresher, you don't have to know all of that. You just have to know some programming language. You need to be able to think logically. You need to be able to decide that this is how my algorithm will flow, or this is how I'm going to process it. And the language skill will come parallelly on your job. So going back to my career path, 2007 to 2014 was a time when UVM, which is a universal verification methodology, which is based on System Verilog, is something I picked up. C is important. Okay, there's a comma missing between C and scripting. C is something that is very important for a verification engineer if you're working on chips that are processor-based chips. In some cases, when it's not processor-based chips, then of course it's not C. You need to understand protocols like a SPI protocol, serial protocol, or I2C. I don't know whether that is something which is familiar to people, but all that is something that you will learn on the job. Scripting comes in useful. Gate level simulations is something Janani talked about. It comes at a point when you start in that gray area where you've finished synthesizing it, you've done your place and route, but you want to feed it back into the simulation and see whether timing holds. So gate level simulations come in there. Formalin is another methodology. Silicon debug is a skill which you need, which I had picked up at that point of time. And of course, parallel to tech skill at that point, I started mentoring 1 or 2 people. What I'm trying to say here is look out for the skills. And at this point of time, this is when you can decide that I want to either pick up UVM and be a UVM expert, or I want to pick up formal and be a formal expert, or it could be that I want to become a people's manager. If you find, like I have found that my strength has been in people management, in which case you grow on the managerial ladder. If you pick up a skill and you want to go even more in depth into it, then you could actually get onto a technical ladder. then 2014 to 2020. One of the things I was trying to also say here is verification is so large and it's constantly evolving because of the designs that you have to work on. VLSI design has been around for 60, 70 years or so, but verification has come into being only in the last 20 years, a little more than 25 years maybe. So mixed signal is something that is a choice if you are good at analog, because it's a very niche skill and there are not too many companies who work on the mixed signal side of things. Analog devices has some chips where, as I said, the digital content is lesser, but there are more analog there's more analog content. So you have to, in mixed signal verification, you actually have to check how, firstly, you have to model the analog into a higher level modeling language to make it faster, because if you do your simulations in schematic, they are very slow. So you have to first do the modeling, then you have to put the digital and the model together and then check the specifications that I was talking of earlier. The other things that are coming up now are power-aware simulations, because chips have low power modes where a part of the chip is turned off, another part of the chip is turned on. So if the part of the chip which is off starts affecting the other part which is on, then potentially you could completely use the status of the domain that is supposed to be working. And finally, once you have grown in a particular domain, whether it is verification or something even more specific than verification, if you get into the people management side of it, then you need to start picking up non-TV skills at a certain point of time, much later on, where you will have to lead a complete team of people doing chip design, doing analog design, doing front-end verification, and doing verification itself. So you'll have to be able to lead that entire team. And one thing that has always been useful is asking questions throughout your career, whether it is as a fresher, because that is the time when you're understanding various things, but even more so when you grow into a larger role, sometimes you have to ask questions just to be able to figure out whether things are to understand things that you don't have hands-on experience on, because at a certain point of time that will clash, where either methodology has moved on and your hands-on experience was on an older methodology, or you're now responsible for a bigger things, and you didn't work on design, you didn't work on front-end synthesis. So that is how the career path of a verification engineer who gets into people management looks like. Now, how do we start off? Can you go to the next slide, please? So for a fresher entering a digital verification role, all you need is the stuff that you learn in college: digital electronics and computer architecture, and software scale programming in any language. Over and above this, the Verilog, or the system Verilog, all that you will learn on the job. But as a fresher, the only thing we expect is you understand your digital electronics well, you understand setup and hold, how flip-flop works, questions around, using only a D flip-flop, how can you make it into a T flop, all those kind of basics which are there, which you have in your courses. That is the only thing that is important. Computer architecture helps for a verification engineer because we are generally the ones who own the chip environment. So if it is a processor-based environment, you need to be able to handle compilers. You need to be able to set up the complete tool set for the chip so that you can, take C code or whatever code, compile it, generate a binary, and then load it into the uh, memory. And further, in debug also for processor-based chips, it comes in handy when you're trying to debug and figuring out, whether your stack has gotten corrupted or your program flow went off because of a corrupted program counter, or when did the interrupt get called. So those kind of things are useful. Again, whatever is there in your course, that is it. It's though Palnitkar and all that, I remember even we followed. It is a very old book, and it was very useful to clear basics. But what I'm trying to say is, we're not looking for, very edge level technology. All that we expect for a fresher, we will work, invest, train, and get you to understand those things, depending on what job you enter or what business unit you enter. So skill growth on verification, it's, as I said, the methodologies are very varied. So depending on which side you go into, the skills will be different. In a lot of companies, each one of these lines is a separate group who does. There'll be one group who does functional verification, one group who does formal. There'll be some people who specialize in emulation platforms and FPGA. Mixed signal verification is very, very niche and not very common to even find. But that is another one. Power aware verification is awareness of low power modes and things like that. So what I'm trying to say here again is the verification field is very large. So depending on where you get into, you will have to decide that I want to specialize further in this particular skill, or I want to, in my case, I had the opportunity to dabble in almost all of them because of the chips that I ended up working in, where there is a bit of analog, there is low power, and entire signal chains that we had to work on. So if that is the kind of aptitude you have, where you like to work on multiple things, then there are very few companies who do something like that. Analog Devices and TI are some of them, a couple of them. I don't think many other companies have that breadth in methodology. There, in the Qualcomms and the Intels, the challenge there is this large digital and all this complex digital logic, which does huge amounts of computations, and the bandwidths and speeds are unimaginable for anything which is closer to the analog side of the world. The last thing in the skill list I kept as domain knowledge. Now, this domain knowledge is again something that you pick up on the job, depending on what group chip that you work on. So earlier I used to work in DSPs, which are just processor-based design. So I understood general purpose DSPs better. Right now I work in a group which does BMS systems. So we work in, we have chips which sit close to the cell in electric vehicles, sends the cell another chip that drives the first and elicits information from that and then passes it on. But this domain knowledge is something that you will start building from the day that you join the group. And it's very important to build this domain knowledge to understand what you are verifying for. What is your end product going to be? How do the people who get the chip use your chip? Because the kind of use cases that you'll write for your verification will depend on that. And again, this last career growth path I have put because there always is this question that I've heard or a myth that I want to bust, that verification, you get stuck at a ceiling somewhere. And it's not that. Verification is a completely parallel skill, a completely parallel group. So you go through an entry-level engineer, get into senior engineer roles, and then if you get pulled more towards specific methodologies, or you're able to drive specific methodologies to higher levels, then you get into a principal or staff engineer. And in case of analog devices, we have one person in Bangalore who's become an ADI fellow. He's from the verification side. So typically IEEE fellow, ADI fellow, that is a level of recognition of the person's work. So this person is the first verification engineer globally across ADI Global who has become a fellow. So verification is a very important skill, and companies are trying to pull people into verification. I think the requirement for people across all jobs as in the VLSI industry has really grown. There aren't enough people getting into VLSI jobs, be it design, be it verification, or back-end, front-end, everything. So it is something that everybody's looking for. But having said that, verification teams are growing the fastest, and they are at that cusp of becoming a pillar of the entire design process and of the company in general. So yeah, I think that's all I wanted to say. Trying to sell verification. Yeah, open for any questions that anybody has.
We have a question.
Okay. Yeah, how are the job roles of verification and validation different? So again, when you speak in English, they seem to be the same, but what we see is verification is something that is pre-silicon. So you are coding in System Verilog, which is also the language that digital designers code in, but your System Verilog has features for randomizing. It has a specific set of features and follows a methodology called UVM. But primarily it is coding and it is pre-silicon. Validation is something that comes up post-silicon. So validation engineers have the chip in hand. They get into the PCB design this is going to be the PCB. These are the features that will have to be exercised. They will code in C, and they will use it like how a customer would use it on the bench. They'll do characterization. They'll check if there are bandwidth issues or anything which is related to if there are analog bits in it. They'll do the ADC, INL, DNL, again characterization. So validation is something that happens post silicon on board. Verification is something that is pre-silicon. Generally part of the design team, loosely. Sure.
If you have any other questions, please do put it in the chat box. So thank you, Shreya, for that very extensive talk about VLSI verification and what a career path would look like in verification. Now moving on to the next topic, which is back-end VLSI design. we have Nandita who will be talking about this field. Over to you, Nandita.
Hi, am I audible?
Yes, you're audible.
Okay, yeah, that's great. Let me just try. I'm not really sure how good my internet speed is. I'm hoping it doesn't fail on me. Okay. Oh no, there's no purple light in my room. Okay, I think I'll go ahead like this so that you don't have to like see one, black shadow kind of thing of me. I'm so glad that I am doing this right now, and for all the hype that was given by all the speakers before for back in VLSI, now I'm feeling very fancy doing this. But I must just give a heads up to all of you that I'm a novice in this field, and I started out like how do I say, like last August. So whatever I speak is just from 1 year experience, which includes like a grad school and like a few months of my internship. Just to give some context, I am in University of Minnesota doing my master's in VLSI, and I'm currently interning with NVIDIA, and it's just been, I think, around 2 months. So I don't really qualify myself to to talk so much about this, but yeah, anyway, now that I'm here. So as far as I have understood and thought about this and discussed with my friends and peers and people at work, I have understood that back in VLSI has three main aspects to it, or three major groups to it, which mainly involves circuit design, physical design, and a methodology team, or sometimes we call them PD Meth or we call them PD CAD. So these are few things which I have come across different when we look at different roles, especially. So in circuit design, what people primarily work on is how to develop circuits for SRAM design, or like how do you design an SRAM memory parts and things like that. In physical design, that is what I'm working on. I would say it's more like bringing, how do I say, like some physical aspect to whatever you have done in digital design. So I think just like Janani was speaking about it earlier, and she was talking about how you write the code and you verify, and then you go back and forth, back and forth, back and forth. And then somebody has to put all the transistors to it. So if you ask your code to do something, then it has to be physically possible to implement it so that you can use the logic on, like, say, your system, your phone, or any other device that you're holding and using right now. And finally, methodology is a domain which mainly involves like developing flows that will control how the chip is transitioned from basically front end to like the final physical output, or the tape out as they commonly call it. Can we move on to the next slide, please? Yeah. So this is an extension to what we saw a few slides earlier, where we talked about the front end aspect of it. And like Janani said, I think it's a constant dispute as to whether synthesis belongs to back end or whether it belongs to front end. And it's a very company dependent thing. So for most people, you just get a netlist. So how I would like to answer these, very few, three small questions which I've put up here, because these were some questions which really bugged me when I started out in this, in this domain. So you come up with an RTL design. Okay, that's great, wonderful. Now, what do you do next about it? Like, how do you decide what goes on the chip? How do you decide what is the area? How do you decide where you place what? What is your logical hierarchy? Do you want to do like, how do you fit so much into that small space? So I think that really boggles our minds. Like, how they're talking about 6 million transistors in what, like a few millimeter square area, like how? And doesn't that lead to a lot of problems, like maybe say IR issues, heat up issues, and things like that? And what is your work around that? So for this very reason, they have like a fixed set of steps that they follow through, so that it does what it does and what we expect it to do. So I would, as much as I would love to keep talking about this, I think I would maybe give like a very brief analysis of what happens here, so that it makes a little more sense rather than me being very vague about it. So first, they do something called as floor planning for the chip. So once you get the dimensions and the specifications, the next thing that you do is you'll have some major blocks that go on your chip, which are called as macros. And for example, this could be like, say, your RAMs, which were designed earlier and pushed to your team by the analog design team. So you basically fix the big things in first, and then you go for the smaller instances in your design. So you fix the macros. And the next big thing which you and I can think of is the power should reach all these devices, and there shouldn't be much drop, or we should avoid it as much as we can. So your priority would be to make sure your power is routed properly. So all that happens in the floor planning step. And if you think about, if you go into the nitty gritty details of some things that happen in floor planning, I think what really blows my mind is the extent to which people think and have backup plans for almost everything. I wish I had that kind of planning, which I think I never had. But they even place cells called as pair cells inside your design, just in case, like how we had a talk about verification and validation, like just before mine by Shreya, where she talked about extensively about the difference between verification and validation. So these pair cells, in case like at the very end of it, and you want to like you find out, oh, some logic is not working. Now, just like on her slides where she was talking about the cost involved with this, you can't really backtrack and trash all the chips that you have gone through for the effort of going all the way through. So you have some backup plan for that as well on your design. So all these things will be placed initially during floor planning. Then they go to something called as placement and clock tree synthesis. So placement is where you place all the other logical cells in your design, and there will be some form of hierarchy for this part of it, and how do I say it? It is done by various methods. There are different things that they do about it. They sometimes place cells and they do floor planning together. So I think that would be me taking too much of a deep dive into it, which I really don't want to do right now. So and bore you with the extensive details. But maybe if we have questions, we can surely go through that. And just like I said, just as much as power is important, another thing which is very, very important is making sure that all your sequential logic part in your design is properly clocked. Now, this is where clock tree synthesis comes in, and making sure your clock has the least latency and it doesn't like really mess up here and there. It is very important that you route that in the beginning as well, before you go about connecting the rest of your logic. And then you go to routing, and then you do something called as timing analysis. Now, to be very honest, this picture doesn't do complete justice, but timing analysis is done after different stages where they're trying to check if the design is meeting the timing specs that you want it to meet. So here you will check, there are some things called a setup and hold, and you do different kind of analysis, including transition analysis. And then you go to physical verification, where you actually verify your design. You go through something called a DRC, which is like design rule check, where you'll have a set of design rules. So you can't just do whatever you feel like to the design and expect it to be manufactured. Right now, we are at the 5 nanometer level for so you would have come across the term called as the channel length. Now, as much as it is a myth that, it's a 5 nanometer channel length, which is a marketing gimmick, as my professor says, in every class and at every opportunity he gets, at 5 nanometer level of technology, it is going to be so, you can't, it is not very easy to basically manufacture that physically, like, at the foundry. So there are certain set of rules which has to be followed so that it is easier and, you have a better throughput from the manufactured products. And so you go through DRC, there is something called as LVS, which is layout versus schematic. So you have a schematic for your design, and you also have a layout now, which has the multiple layers and the masks and all that. And now you are trying to check if they're both same. Now, one thing which I would like to say is, I sometimes, okay, to be very honest, I have wondered why so many checks. There are so many checks done at so many stages, and the number of people and the number of checks that have been done is just, sometimes I would say beyond me. And like the company that I'm currently working for, they do a final, they just do an eye check as well, like, where they sit down and somebody is looking at all these million connections and all these VRs, and then they are giving off their check as well. And I wish I had quarter of that patience, but yeah, I am hoping to develop that as a skill through my career here. So that is another, like, there are so many checks done at so many stages, so that once it goes to the foundry, we know that whatever is going to come outside the foundry is definitely going to work, other than, some issues at the foundry or like some manufacturing level problems. Apart from that, we know from our end it is going to work. And then finally they go into a round called as tape out. Now, where do I come as a physical design engineer? Now, obviously, I am not definitely sitting and placing the cells one by one, or doing anything manually. I would say I'm more of doing the press button work of running the different runs. I mean, all the way from floor plan to physical verification, and then I'm checking my design. So, as a physical design engineer, I think your primary skill that you're going to develop is debugging. So I have this running joke amongst my friends where here at the U, where they call me Sherlock, because if there is an assignment that is sent out, 100% Nandita is going to find a problem in it, and then she's going to ask questions which are just going to make us feel like, oh no, why do we even know her? So I'm so glad I ended up here, because I think having that name Sherlock has like really helped me, because I definitely find problems even in the simplest of things. And for people who know me from my undergrad, I think they will realize how much I used to complain in lab about how something just doesn't work. Like, when I touch it in the lab and I just don't know why. And I am so glad I went through all that, because right now I really have learned to have a sharper eye and keep looking for problems in, job interesting. Yeah. Can we go to the next slide? Next slide, please. Yeah. Oh, I'm so proud of that, small cartoon which I have on top. But yeah, so some of the courses you might really want to look out for if you're planning to like do some self-study, or if you are planning to do a master's and you're looking at courses that various institutes or universities are offering. These are some things which you would want to look out for if you're interested in backend. So one would be a course in VLSI design, and I would really, really recommend anybody who wants to do backend courses to come to University of Minnesota, especially if you're interested in, like, say, circuit design, or for that matter, PD methodology, because I feel all these three, according to me, all these three go hand in hand. So one small example which I can give is, in your coursework, you would have learned about something called as, how do I put it? You would have come across a term which is called as power dissipation in circuits, and then you will be learning different aspects where you'll talk about leakage power, dynamic power, static power. So you learn this at a circuit level, and as a PD engineer, you're looking at this on a top or a high level, where it is more like, okay, there is a leakage power issue in this region, and what can I do to solve it? So I would say any design course, it will really help you as a PD engineer, or as a circuit design engineer, or for that matter, even as a PD methodology, if you're working in that field as well. Another thing which I would ask you to really look out for is courses on VLSI design automation. And many people ask, like, okay, if I'm going to be a circuit design engineer, why would I even want to look at, like, say, design automation? I would say design automation is, what is making yours and my life easier. So as a design automation person, you'll be working in close, basically hand in hand with the tool. And it's only because of the design automation engineers and the advancement that they have made that, we are able to do what we have done. I feel like it's a very personal opinion. So you shouldn't quote me on this. And I would say taking up, you must also maybe have a look at courses which have, help you familiarize yourself with the various tools in PD, like say Innovus, ICC2, Seahawk, Tempest. So these are so many tools, and it is definitely going to be very, very challenging if you want to be a master of all of these. But for sure, you can have look out for these and see if they're offering some hands-on experience for at least one of these, like say just Innovus, and you just learn how to do floor planning on it, or maybe just go over the flow on through Innovus. So that'll be something that you might want to look at. And again, there are specific courses for static timing analysis where they teach you how to solve setup, what is setup, how to solve hold, what is hold, and all the other things associated with it. And definitely, I think, as far as I know, there are courses online available for understanding the physical design flow and what it encapsulates. And you should surely have a look at those as well if you are really, if you're really keen and interested in going in that direction. But again, just after you finish your undergrad, I don't think any of us would really know what is back-end VLSI. And if I were to be very, very honest, I came here only for one professor. I did not apply to universities with that intention of coming here, but I chose to come here finally only because of one professor. His name is Professor Kirthika. As much as he has made my life a living hell for the first 6 months, from September to December after coming here, given me many sleepless nights, extremely thankful to him, because I think only because of him, I've been able to understand all this. And I have never been able to attribute my success to a professor as much as I've been able to attribute it to him. Yeah, I think that's about it. So if you have any questions, please feel free to, ask along, or maybe you can get in touch with me later on and we can have a discussion as well.
I think since back in VLSI is such a new field, looking at it from an undergrad perspective, I think that's why people are not asking questions.
Oh no, I know it's. I think many people don't even really know about it until they come here. So I think it's like jumping into the dark end of the sea. So I would say, like, obviously, I don't feel bad at all, because if I were to listen to myself speak, like a few years back, I would be like, huh? No, I don't have any questions. So yeah, but if at all you decide to apply to universities and you're thinking about, a constant confusion which all of us have, is it front end or back end or what to do? I think you can always reach out to me if you want to just discuss about, what are the options in back end and what does it really mean to be a back end VLSI engineer.
Yes, sure. So thank you so much, Nandita, for that extensive talk about back-end VLSI. I personally learned a lot about back-end VLSI because, like, even I just finished my BTech, so even I didn't have much idea about that field. And I'm pretty sure even all the attendees feel the same about it. So now, moving on to the next talk. So the next talk is about computer architecture, and this will be given by Harini. So over to you, Harini.
Hey everyone, can you hear me?
Yes, you're audible.
Awesome. So before we get started, right, first of all, a pat in the back for all the organizers for organizing the entire mentorship program. Because when I look at it from my perspective, 9 years ago when I was just about to graduate, had there been such a program, right, I feel that my transition into the industry, as well as all my questions about higher studies or not, everything would have been answered in a much more efficient and simpler way. So great job, guys, for doing this. I know that being in the last semester and stuff, you will have other commitments as well. So in addition to that, doing this, it's a wonderful effort. So to all the mentees, one thing that I would mention is that, make sure that you really make use of this opportunity. Ask all your mentors, barge them with a lot of questions, right? So no one is going to say that, hey, you are wasting my time asking so many questions and so on. So make sure to utilize this opportunity, because like I mentioned, you will be able to feel the effect of this even 5 to 6 years from now on, I'm pretty sure. So make sure to use this opportunity. So before I get started with what computer architecture is, and maybe a small sneak peek into what I do as a part of my work, I graduated from NIT Trichy close to 9 years ago. And I initially took up a position in Qualcomm. I worked with them for close to 2.5 years, where I was primarily doing performance modeling as a part of the architecture team. As well as, I also had a short stint with the VLSI design team, where we were designing, the super cool Snapdragon SoCs that go into the mobile phones. At a point, I got this existential crisis. Okay, what am I doing? What is it that I want to do next? And stuff like that. And that's when I decided, okay, out of every single thing that I've seen during my tenure at Qualcomm, architecture was something that really excited me. And if there is one thing that I want to pursue, higher studies in, it is going to be computer architecture, because I sort of felt that once I get to know the architecture completely, I will be able to jump into any other field, if at all that's required. So I know other mentors might have a different opinion about this, but again, this is my personal opinion. So yes, so I ended up doing a PhD in computer architecture at the University of Michigan, where I was focusing on exploring, when we have these massive large-scale GPU systems with many GPUs, how should the GPUs communicate with each other, and how is it that we can better ensure that as we increase the number of GPUs in the system, the performance scales linearly, or at least close to linear scaling. So that was something that I looked during my PhD, and I just defended my PhD in December, and I just graduated this April actually. And from February, I've been working at NVIDIA. I'm a part of the research division of NVIDIA, and I'm a research scientist with the system architecture research group that explores, basically 5 years down the line or 6 years down the line, what should be the, how to, efficiently build massive, multi-GPU systems, which with high performance, and what are the new applications that we can venture into, and so on. So that's basically a short introduction about me. Next slide, please. So coming on to computer architecture itself, right? So what is architecture, right? So computer architect is one who sits in the boundary between hardware and software. And for example, right, you take your mobile phone and say you play, for example, Temple Run, right? So the way it will work is, okay, the programmer or the coder who wants to design, for example, a game would have, written the game as, say, a C program or a C++ program. And, that is going to be, once you compile it, that is going to be converted into a binary file. And that binary file will finally, end up executing on the hardware. So the computer architect is the one who sits in the boundary between hardware and software. So we basically look at, for a given application, is the existing hardware good enough to get, the maximum performance for that particular application? Or should the hardware be modified in any way to be able to suit an application better, right? So the applications that I've listed here are the applications that I ended up looking at during my PhD. So, there are tons of applications, right, that make use of computers these days. And, here are just a few examples, right? So if you look at every application, every application is going to have its own requirements in terms of, okay, how much memory do I require? How much processing power do I require? And, what are the access patterns of the different, different memory transactions that happen? And how do I optimize my hardware to be able to execute an application in a much more efficient way, both in terms of performance as well as in terms of power, right? So that's what a computer architecture will be, a computer architect will be looking at. Next slide, please. Can you go to the next slide? Yeah, thanks. So as your day as a computer architect, right? So what is it? What is this going to comprise of, right? So whatever set of applications you have, right? So the applications are going to basically translate into a set of compute operations as well as a set of memory operations, right? But what is going to vary between different applications is, how these are interleaved. So how many compute operations, how many memory operations, right? So how do you interleave both the compute and the memory operations and so on, right? So that's how the applications are going to vary in terms of their own requirements. So as a computer architect, what you will be doing is you will be looking at the different applications and deciding, okay, to be able to execute this particular application, and get so and so performance which the user finally requires, because the example that I quoted before, right, in terms of the Temple Run application, once you make a move, you will want to make sure that the system responds in say 0.1 seconds or 0.01 seconds, right, so that your interface is much smoother, right? So given that performance requirement, how should the hardware be designed to be able to get that level of performance, right? So that's what a computer architect will be looking at. So how many computational cores do you require to be able to process the computations? Okay, how many memory do you require, and where do you really place the memory? Okay, if you look at the memory, right now it has different hierarchies, and how much memory should be placed where. Do you need DRAM, do you need SRAM, and how much of DRAM and how much of SRAM, and what should be the memory bandwidth? And okay, if you look at really large scale systems, how do you want the different components to communicate with each other? What kind of protocol do you want to adapt? How do you achieve the different performance goals that are there for your system without breaking the functionality, right? Because there are a lot of tricks that you can play in the hardware to be able to improve performance. But you also need to make sure that the application finally produces the end result that the application developer is looking for. And so these are the different questions that you will be asking as a computer architect. And you will be working very closely with both the software team that looks at, okay, what are all the different applications that we need to look at and how to optimize the applications at a coding level. And you will also be very closely interacting with the hardware team, which is, the VLSI design engineers, primarily, I would say, to try to understand, okay, what are the hardware restrictions that are there that you need to incorporate as an architect to be able to design your systems better. Next slide, please. And in terms of research areas that are there in computer architecture, every single day, right, we see a lot of emerging applications that are coming up, right? So 20 years ago, right, there was I don't think there was any notion of even self-driving cars or quantum computing, for example. And how do you really design your computing systems for these emerging applications? Because like I mentioned before, every application has its own demands in terms of both compute, memory, as well as performance. And how do you meet those applications? And are the existing computing systems really sufficient to be able to meet the requirements of the emerging applications, or do you need to add a special component in your hardware to be able to meet their needs, right? So that's one thing that that you will be looking at. And the other research areas are, even though computing systems have existed from like a long time for even like for like different applications, right? There are like still opportunities to optimize and redesign the existing computing systems so you can perform even better in terms of both performance and power, right? Because sky is the limit when you want to optimize and churn, higher performance and higher performance. And also one more thing that you will be looking at is the last point that I mentioned here, which is hardware software co-design, which is what like many computer architecture researchers are currently looking at. This is where you try to see, okay, how do you basically like design the hardware keeping software in mind, and also design the software keeping the hardware in mind, so that there is better better synchronicity between the hardware and software, and your system performs in the best possible way, right? Because if we look at like the hardware engineers as well as the software engineers, right? Mainly it ends up, at least during my tenure at Qualcomm, I was able to see that, both hardware and software ends up being in, like completely different islands, right? So usually the software cycle in terms of design is like at least a year lagging behind the hardware cycle in terms of like looking at as to like how do you want to design the programming model, how do you want to design the different programmer interfaces for a given hardware, right? So they are usually lagging behind. So hardware would have like moved on to a different chip when the software is right now looking at like coming up with a proper driver software or a proper programming system for the current chip, right? So they end up being in like completely different islands actually, and like how to make sure that there is better synchronicity between hardware and software, right? So that is one more thing that computer architecture researchers are currently like looking at in like in a very large scale. Next slide, please. So in terms of what skills you need to be a good computer architect, you need to know as to how a processor works, and how like a computer system works. From, I would say, you need to know it from top to bottom, right? Because you will be making, so what you will be doing is you will be making changes to the computer hardware in a simulator, and you will be evaluating whether the applications that you want to accelerate are performing better, or are they actually suffering performance degradation, right? So that is one of the major things that you will be evaluating. So you need to know as to like how the existing computer system works, right? In terms of, okay, how does a processor work? Okay, what is translation? What is virtual memory? What are the different levels of memory hierarchy? And what is pipelining? And what are superscalar processors? And so all these concepts you will have to know really well, because you will be making changes to it, right? So without knowing what it is currently, it's going to be really hard to be able to suggest good changes to make to the existing architectures, right? So that brings us to the next part. So whatever new ideas that you come up with, and whatever innovative hardware components that you come up with, what you will be doing is you will be implementing in a simulator, which is in most cases C++ code, where you will be evaluating whether the technique that you design is a good one or not, right? So you need to be really proficient in C++, and you need to be able to do a good job coding. And like I mentioned before, you will be working at the interface between hardware and software. So even though you will be primarily making changes to the hardware, you also need to know to some extent as to, okay, what is the compiler doing in terms of compiler optimizations, and how does a driver work, and what are the how does a driver perform memory allocation, for example, and what are the different things the software stack does, right? So you will have to have like at least some like really basic knowledge about the software stack as well. So I think that's my last slide. So yeah, if you have any questions, feel free to ask. If you want to reach out to me later on, you are most welcome to. And thank you so much for this opportunity.
Thank you, Harini, for that really interesting talk about computer architecture. So if you have any questions, please do put it in the chat box or unmute and ask.
So just one quick thing, right? While you guys come up with a question, one quick thing I wanted to mention, right? So when you come for, say, for example, your masters to the US, right? Even if you end up coming, for example, architecture, and you realize that VLSI is your calling, or even the other way around, right? You come for VLSI and you decide, okay, architecture is something that you like, right? You will have an opportunity to take courses that are specific to that particular area and get a job in that particular domain. Right. So even if you have, for example, a master's in architecture, you can still get a VLSI job. And even if you have a master's in VLSI, you can get an architecture job, right? So if you want to come abroad, right, you don't have to really, think so much about, okay, is this the thing that I want to do? And you don't have to really take the final call before you decide to step in, because there are opportunities to, change and, follow your passions once you come here.
While people think, I think really, this is the first time I've been part of this mentorship program. The professionalism and the way with which it is being done, starting from the kickoff session to having a deck in which you've put in all the names and everybody knows what they're talking about, and conceptualizing the whole thing and coordinating with all of us. I think it's a terrific job. Huh? I mean, I think we lacked these sources of information 20 years back. I'm so glad you guys are doing it.
Thank you so much.
I'm so very happy to hear all the mentors here. I think being a novice in the industry, I kind of learned a lot from all the seniors who spoke right now. So thank you so much. It's been very enriching.
And just to the mentees, I don't know how many of you are in final year, how many are in third year, but if there's anybody who is in third year looking for internships, do get in touch. And anyway, to everybody, I think it'll be good to get in touch. I see some have linked on LinkedIn also, so let's get in touch in any way. But one special note for the third years if they are looking for internships.
Yeah, there are some third years who have joined, so I think they will get in touch with you.
Sure.
So I think they don't have any more questions. So I think so. With this, we come to the end of this talk. I would like to thank all the speakers who have taken time out of their busy schedules to give us such an insightful talk about VLSI and what the industry looks like, be it what a career path in a corporate world would look like, or the various research areas. I personally, as a fresher who is going to join as a verification engineer, I learned a lot today. Like, what hires would look like, what working in a company setup would look like. I personally learned a lot today, and I am pretty sure all the other attendees feel the same. So once again, I would like to thank everybody for joining joining us, and the speakers also for joining us in spite of all the time zone difference and everything. So thank you so much for joining, and yeah, with that we'll wrap.
Thank you, Kirthika, for being a wonderful host.
Thank you.
Yeah, thank you. Yeah.
Thanks, everyone. Thanks, Kirthika. Bye.
Thank you. Bye.
Bye, everyone.